So we looked at how to divide polynomials, and we just saw synthetic division when we divide by x minus something. But what if we're dividing by something with a leading coefficient? So in essence, what we'll end up with is that f of x, our original polynomial, is ax minus b, we'll call it minus instead of plus, times whatever the quotient is, plus that remainder. We saw this in the previous division idea that we had. We'd take f of x divided by q of x. By this binomial, we get the quotient, q of x, and we have a remainder also. So how do we deal with this? Well, let's factor the a off so that it's just plain a, or just plain x. So a times x minus b over a. So now this first factor is of the form that we were able to do synthetic division with. And that's kind of nice. But what happens now to the rest of this? So this is what we're dividing by times q of x plus the remainder. So this is really equal. So this is really equal to this binomial a minus b over a times a q of x plus r. So what does this mean? What does this tell me? Well, if I'm dividing by the linear factor that has the leading coefficient, something that has this a, we can factor that a out and then divide using our synthetic division. But we can see here that the quotient will be this many times. It will be a too many times too big. So now you have to divide the coefficients by that factored value to get the real quotient. The remainder is not affected. So let's put it into practice here. Okay, so I'm dividing by 2x plus 3. Let's take and divide the 2 out. So this becomes x plus 3 halves. You don't believe me? Divide that or distribute that. So now I'm in the position where I can do synthetic division. So the number that goes out here is negative 3 halves. The coefficients inside are going to be 2, negative 7, 14, and 5. We drop the 2 down, and now we multiply. Negative 3 halves times 2 is negative 3. And then we add, we've got negative 10. This is going to be positive 15. This is going to be positive 15. And then we're going to multiply by negative 3 halves again. So now we're adding, we get 8. Multiply by negative 3 halves, and we get negative 12. We add again, we get 2. Multiply by negative 3 halves, we get negative 3. So our remainder is 2. So what we now know is that when we divide this by x plus 3 halves, I get these numbers. But I really want to divide by 2x plus 3. So my new polynomial, it's going to be x to the third. I'm dividing all of these by 2, this number, minus 5x squared plus 4x plus 1 plus 2 over 2x plus 3. This is our remainder. So there's our quotient with the remainder when we divide by 2x plus 3. All right, so here's a fun little problem. We want to find the remainder when f of x is equal to x to the 2011th power minus 3x squared plus 2x minus 2. When we divide that by g of x being x squared minus 1. Okay, so picture dividing this long division style by x squared minus 1. We would need to do x to the 2011 plus 0x to the 2010 plus yada, yada, yada. And we'd have far too many terms to actually do anything worthwhile with this in any reasonable amount of time. So what can we do? Well, we're taking f of x and dividing by g of x. And we know that when we do that, the remainder will always be of less degree than g of x. So we know that we could write f of x as g of x times some quotient plus a remainder. And in this case, since we're dividing by a quadratic, it is okay to say that this remainder has to be a linear function. Now, is it possible that the remainder could be a constant? Sure, that would just be if this a value was 0. But in general, when we divide by a quadratic, the remainder is going to be linear in nature. So what we're going to do is let's find f of 1. Why f of 1, you might say? Well, f of 1 is a 0 of the denominator. So f of 1, if we plug that in, we're going to get negative 2. So f of x equals g of x, so g of 1 times the quotient evaluated at x, at 1, plus a times 1 plus b. Okay, now let's look at why this is good for us. Why did I pick 1, and why is it important that g of x is a function that has 1 as a 0? Well, look at this part right here. That effectively goes to 0, becomes 0, which leaves us with the equation 2, negative 2, equals a plus b. You might see where I'm going now. There's another 0 for g of x. Let's find f of negative 1. F of negative 1 is negative 8. And that's going to equal, by this decomposition, g of negative 1 times q of negative 1 plus a times negative 1 plus b. That stuff goes to 0. I now have negative 8 equals negative a plus b. Solving this system, we get that b is equal to negative 5 and a is equal to 3. So my remainder is 3x minus 5. So there we go. A very alternative way to think about finding a remainder. So we're now going to deal with complex zeros. We've been dealing in the realm of real number zeros, but that's not always the case. So here's a very simple function that has complex zeros, and we can solve for them easy enough. So we want to set this equal to 0. Subtract 4, x squared is negative 4, and then x is plus or minus 2i. And what this really is, it's, if we think about it as complex number, we have 0 plus 2i, or x equals 0 minus 2i. And what do we call these two things? We call them conjugates. Complex zeros for a polynomial will always come in conjugate pairs like this. And we're going to use that in the next example. So we know that 2 minus 3i is a 0 of this. We want to find the remaining zeros. Well, if 2 minus 3i is a 0, 2 plus 3i is also a 0. And how many zeros are we looking for? Well, since this is a third degree polynomial, we know that there will be 3 third degree polynomial. We know that there will be 3 complex zeros. Now what we know is since there are two complex ones that involve an imaginary part, that third one has to be real because it can't have another conjugate pair. So what do? Well, remember if like 2 is a 0, x minus 2 has to be a factor? Well, if 2 minus 3i is a 0, x minus 2 minus 3i has to be a factor. And then x minus 2 plus 3i has to be a factor also. And then finally, some other factor, we'll call it ax plus b. It's going to be some other linear factor giving us our third 0. So what do we do here? Well, let's expand. Let's take these two and expand them out. X squared, just to make this a little easier, let's send this negative through. Minus 2 plus 3i, x minus 2 minus 3i. So x squared minus 2x minus 3xi. Now we go to the minus 2 and distribute that. Minus 2x plus 4 plus 6i. Then we distribute through the 3i. Plus 3ix minus 6i. And then we have minus 9i squared, or plus 9. Now let's combine our like terms, and then we'll look at what we're left with. So now we have x squared. The 3ix's cancel out, the 6i's cancel out. We have minus 4x plus 13 times ax plus b. Okay, I'm going to further expand this. I'm going to keep multiplying, and then I'm going to compare my coefficients to the individual terms. I could do long division at this point. I could take p of x and divide by this quadratic to find my remaining factor, but I'm going to do it a little bit differently, step out of the dividing realm for a minute, and expand this. So we have ax cubed plus bx squared minus 4ax squared minus 4bx plus 13ax plus 13b, and that has to equal that thing there. So how does that help us? Well, let's equate some coefficients. The constant term, let's start there. 13. Here's my constant term. By this reasoning, b should be 1. Let's go through and see if this works out. Let's jump back before we can check these other terms. Let's go to the cubes. What does a have to be by this reasoning? A should be 5. And now we can look at the other pairs of terms and see if we do get what we needed. Look at the squares. 5x squared, sorry, 1x squared minus 4 times 5x squared. Oh, that's negative 19x squared. Good stuff. And then we can do minus 4 times 1x plus 13 times 5x, and we find that we get 61x. Good deal. So expanding it out this way and then comparing the coefficients of each term to what we know back here, p of x, is one other way that we can find the a and b. So what we now know is our missing factor is a is 5x plus 1, which means our missing zeros, we want to set that equal to 0, x equals negative 1/5. And there we go. There's our missing 0. Like I said, we could have done long division at this point to find our missing factor, but I chose to go a different route. Multiple approaches to the same problem.